so what I'm going to do today, we have new material, but I also want to review what we did last week that you watched the videos about. I will use examples, right? The most important is that you know how to solve problem. So I will start with examples to review some important concepts. So some of you, maybe you think that it is too easy, but still make sure that you understand everything, right? So the first thing that we have done was changing basis. Okay, so let's just go directly to the example. So let's say I have a state psi. This is a general state, right? But now it is specific. I write it as 1/3, 0 plus 2 square root 2/3, 1. Okay, so what basis are we using now? 0, 1. Very good, right? So using the 0, 1 basis. And this is how many qubits? 1 qubit, because it had two bases, 0 and 1, right? Okay, now this is given, right? Let me say, okay, I have a state plus equal to 1 square root 2, 0 plus 1. We discussed in last lecture, last week, right? Minus equals to 1 square root 2, 0 minus 1. This one we still have not started talking about the real qubit or something closer to quantum computing, but this plus minus basis, plus and minus, turn out to be something we call Hadamard basis, right? And it is a superposition of 0 and 1 in this way. Now this is just given, right? Of course, later you will appreciate why they are written in this way, what's the significance on broad sphere, but this is given. Is that okay? I just teach you English, what is 1, 2, 3, 4, 5, and then now you know how to write it in Arabic, 1, 2, 3, 4, 5, how they are related, something like that, right? So, okay, so this is the basis. Then I want to ask, how to represent psi, right, in the new basis. In plus minus basis. This is given, of course, sometimes you need to check if this basis is orthonormal or something called complete, which we will study later, but assume they are normally behaving basis, right? So we just want to practice the concept. So how do we do that? Well, okay, he said inner product of, okay. Uh-huh. So you want to do inner product between plus and the state? Okay, so he's a little bit ahead. We are not there yet. You will use this to do your assignment. That's excellent. The way to find it. We will do something simpler, but you are right. Do inner product, but we are not there yet. You are correct. And that is the right way to do it. Okay, good, very good. Now, but what we can do is express 0 in terms of plus and minus, right? Then I will get this one in terms of plus and minus. Okay, so if that is the case, then what do I do? So first I need to find the relationship. So if this is equation 1, right? This is equation 2. I will just, let's say I just multiply square root 2 to equation 1 and then add it to square root 2 times equation 2. So what am I trying to do? So let's look at this one. I multiply square root 2 to plus. All I'm doing is just solving for variables. Is that okay? Just solve variable using two equations. Treat this as a variable. This is A, this is B, this is CD, this is CD, right? So now you have A in terms of CD. Now I want to express CD in terms of AB. And that's what I'm doing. So I'm just trying to solve the variable, but you need to have this skill right with you. So this on the left, right, it is just square root 2 times plus, and then plus square root 2 minus. Do you see what I'm doing? square root 2 times plus, and then add to square root times minus. Is this okay? And it must be equal, the right-hand side must be equal to this term plus this term, right? So then it means this one equals to 0 plus 1 plus 0 minus 1. Do you see that? Let me repeat again. I multiply left and right by square root 2. So this is square root 2 plus, and this is square root 2 minus. I add these two together is equal to, I adding these two together, right? So 0 plus 1 plus 0 minus 1. Any questions? I want you to understand immediately, right? Don't say, okay, I go home and read it again. Usually you don't have time. So let me know you have questions. And this class, yeah. Oh, do you mean this one? It's just the way I label the basis. I just label that this one has a plus and minus basis. This one? Yeah, so I just the way I label it, I put a slash for between every basis state. Yeah. He asked why I have this slash. It's just a way I name it. Okay, A slash B. It's not operation. I just say this basis has these two basis state. Good question. Yeah. Okay, is this okay? Right? I know it's very simple, but I want you to follow instead of saying, let me go home and think about it again. Right? So what is this? This gives us what? On the right, this is 2, 0, right? On the left is square root 2 times plus minus. And this gives us 0 equals to 1 over square root 2, 0, plus minus. Is this okay? Just a shuffling of variables. Okay, and then the next one, you just continue to solve it yourself because of time. Similarly, you need to go through this yourself, okay? 1 equal to 1 over square root 2 plus minus. Is that okay? Yeah, so this one you trust me. So as a result, what is psi? Psi is going to what be 1 over 3, but then 0, right? What is 0? 1 over square root 2 plus minus, and then plus 2 square root 2 over 3, 1 over square root 2 plus minus, right? Very confusing, but that is how it works. Psi equal to 1 over 3 amount of 0 state plus 2 square root 2 over 3 amount of 1 state. I just copy this to 1 over 3. But what is 0? We already say 0 equal to 1 over square root 2 plus minus. Right? I just plug in this 0 to here. And then this is 2 square root 2 over 3. I keep it. But then what is 1? 1 is just 1 over square root 2 plus minus. Right? So when you do this, just remember, treat them as a variable. Again, if you treat this A, B, C, D, then that's what you do for system of linear equation. You know how to do that already, even in your, yeah.
The new basis also
It is also orthogonal, so we have not proved it, but I give you. Very good question, right? So this is a well-behaving one, is orthogonal and also complete. Orthonormal, not just orthogonal, orthonormal. Okay, now and then all we need to do is just play with the math. I group the plus, so you need to be very familiar with this, right? Plus has what? I have, I will do some simplification first, right? This square root will get cancelled, and then I have, what do I have? 1 over 3. 1 over 3, and then I will do square root 2, right? Plus 2 over 3. You can do a little bit more simplification. Maybe you can factorize 1/3 out. But this is the coefficient for plus. Am I right? How about minus? What is the coefficient for minus? Over 3 square root 2 minus 2/3, right? Because they are exactly the same. When I group plus and minus, the only difference is this is plus, this is minus, right? So I have 1/3 over square root 2, and then minus 2/3 for minus. Is that okay? So let me quickly ask you, what is the probability of measuring 0 for this state? 1/9, yeah, 1/3 square, right? Now, but if I try to measure in the plus minus basis, what is the probability of getting plus? You don't need to calculate, just tell me the square of this term, right? So now you see that for the same states, I measure in different bases, I will get a different probability. Okay. Now then, naturally, this one is a normalized vector. I did not tell you. You can try that because 1/3 square equals to 2 square root 2/3 square, the whole thing square. Because this is 8. This is, right, if you do the square. Okay, so the question is, let's check. So I did a transformation. I hope that my vector is still normalized. It means that the probability of measuring this basis is still sum to 1, right? I don't want to, after a change to another basis, it is not sum to 1. That's not physical, right? So let's check the normalization. So can you tell me how we check it again, someone verbally? So it's the new. How do you check for normalization? I kind of said that already. Okay, take inner product of itself. That is correct. So, yes. So let me rewrite what we got from the previous slide. You're right, take inner product of itself. But because we already know what is the meaning of taking inner product of itself, can you jump directly to the numerical calculation? So very good. He said linear product, and then he said transpose, and then you do it. And if you really go through that process, what are you trying to get to prove? 1. What is equal to 1? Sum of coefficient, the norm. Yeah, very good. Norm equal to 1, or the sum of the coefficient square equal to 1. Okay, they are all interconnected, right? So let's check. How do I check? 1/3 square root 2 plus 2/3 square times 1. I just use square because these are all real numbers. Okay? So to save time, I will just say that this equal to 1. Try to check it yourself. You need to really be familiar with this calculation. But just be careful. It's easy. You just be careful. A squared plus A plus B squared, right? Maybe I give you a hint, right? This equals to 1/3 square root 2 square plus 2 times 1/3 square root 2 times 2/3 times 2/3 square. That is the first term, right? Second term is minus. So you see that the first term is the same, but this is minus. And naturally, these two terms got canceled, right? This one, because one is plus and one is minus. And then you do the calculation. You find that is equal to 1. Please practice it. I understand this is like middle school math, but the point is you need to be very familiar with it. You don't want to make mistake or slow you down during exam, right? You want to solve a bigger problem. Okay, that is check normalization. Again, I acknowledge that you just say that we should do inner product. That is the exact definition. That is what you need to do, right? And when you do inner product, you do a row matrix times the column, row vector times column vector, which is the same as this one eventually, okay? And you want to check that the sum is equal to 1. Any questions? This is a review, so if you have a question, you should say it. Okay. Okay, then let's talk about vector normalization. Last time, in the last lecture, we also talked about vector normalization. The reason we normalize it is usually because after measurement, you collapse to a certain basis. And then there is some disconnect between quantum mechanics and its formalism. That is a part that is difficult to understand. After we measure it collapse, the math will not work. We're just missing, it won't sum to 1, right? We need to normalize it. We need to do the normalization to make it work. Now, for example, if I give you a vector psi equals to 0 plus 1, is this normalized based on we just discussed? No, right? Because psi inner product with psi, now I'm going to use what you said earlier, equal to 1, 1, 1, 1. Am I right? 1, 1? Should it be 0, 1 or 1, 1? 1, 1. Because it's about the coefficient. Okay? I have one part of 0, one part of 1, right? So what is this? 2, thank you. 1 times 1 plus 1 times 1 equals to 2. Is this normalized? No, okay? So let's normalize it. We already discussed how to normalize it in the last lecture. You try to appreciate the equation, but at least you need to know that how to normalize it is by the normalized vector equal to original vector divided by its long, by its length. Which makes sense, right? If you are not too long or too short, I just divided by your length, then you will be normalized, right? So what is the length of a vector again? You just told me there is the inner product, right? And then we take the square root because inner product gives you the length square. Okay, so based on this, what is square root psi inner product psi? We just calculated. Thank you. This is just square root of 2, right? Then I plug in. If it is still confusing for you, doesn't matter. Do it step by step. Insert psi into the denominator and divide this by 2, right? And that's it. This one is a normalized vector. Do you remember this is equal to what also? 0 plus 1 divided by square root 2?
Plus.
Basis plus, right? This one. So this one is, you're going to deal with this a lot throughout the course. And in quantum computer, just every day you talk about 0, 1, or plus minus. Okay, so you need to be very familiar with this. This turned out to be plus. And then you can also ask yourself, does that make sense? It means the plus is normalized. Yeah, because just now some of you asked me if plus minus is of a normal basis. I say yes. And plus need to be unit length, right? So that's how you check your knowledge and your derivation. So this makes sense again, right? Because this is normalized. And yeah, they are all consistent. Okay. So we talk about vector basis change. Right, we have not talked about using the inner product method, but here just a simple one, just substitution of variable. How to normalize it, how to check the normalization, and they are summarized here. Now, and then we also discuss the Pauli matrix. So Pauli matrix, so now I want you to always ask yourself when you see a symbol, is this a scalar, which is number, can be complex. Is this a vector? If you write in the column matrix form, it will be a column or a row, which are the bra or a cat. If not, you ask, is it an operator? Operator is a matrix, right? So here is a three very special matrix called polyspin matrices. We don't need to understand what they are now, right? They are very important and critical. But for now, we just treat them as some very special matrix, and it's easy to memorize. Try to memorize it. Sigma C is what diagonal, 1, -1. Sigma X is like off. I don't know how to say it. Another side, diagonal, 1, 1. And Y is like X, but it's I minus I. And you can think of a way to memorize whether minus I here or I here. Someone told me, okay, just treat minus as something smaller. And so smaller thing will float to the top. Okay, that's how I memorize. So I always remember negative is on top. Right? You think of a way, find a way to memorize it. It is useful to memorize this, okay? Now what are these? Because if you have a matrix, you need to operate on the matrix. Again, in physics, what is the meaning of a vector? I say the wrong thing, I say vector. So what is the meaning of a vector? Correspond to the what in the physics? The state, very good, the state. And if you change the state, it means you change the vector. How do you change the vector based on your math knowledge? You change coefficient. How do you change the coefficient? Huh? Yes, you multiply by operator, right? So particularly at the beginning, we say a quantum operation is nothing but just rotating the vector in the hyperspace, right? So rotating vector is nothing but just multiplying by the matrix. And by the way, if you know about this computer graphic, if you've taken classes in there, you know it's nothing but just matrix multiplication, right? When you, like in a shooting game, when you walk to the front, how do they know how to change the scene and your view? It's just all matrix multiplication about how it is rotate and extend or shrink, right? And why NVIDIA is so successful, at the beginning, they have the GPU is to process the gaming graphic. You need to very, very fast. And to do the graphic, you need a lot of matrix multiplication. And matrix multiplication is very time consuming. So have the special hardware, GPU, to do matrix multiplication. And then here came the AI era, the machine learning. They are nothing but just matrix multiplication. And that's why they grab the market and they are so rich, right? So 30 years ago, people would say matrix multiplication is so boring, but now they're trillionaires. So I'm talking too much, but again, matrix is important now. Now you have a sense, you know that each matrix must be correspondence to a operation of a vector. Or just think about rotation of a vector. Because you can rotate a vector, you are doing quantum computation. You will see that later, okay? This free matrix has the so-called anti-commute relationship, which we discussed in the last lecture. I won't talk about this again, but I want to use this opportunity to remind you how to find the eigenvalues and eigenvector of a matrix, okay? So let's look at, for example, sigma y. Actually, this is in your assignment 1, so basically I gave you the answer already. Let's say sigma y equals to 0, negative I, 0, okay? What is the meaning of its eigenvector and eigenvalue? It means sigma y multiply a vector I call E equals to E times E. And here is what I need you to tell me what these are. What is sigma y in terms of number, vector, and scalar, vector, and matrix? What is sigma y? Matrix, right? So it is 2 by 2 in this case. How about when you see this cat E, what is this? Vector, thank you. So it's going to be 2 by 1 column, right? You need to think in this way. And this is, of course, a vector. How about this small e? Okay, very good. Someone say it is scalar. Can this be a vector? It cannot, because vector multiply vector cannot give you a vector. So let's step back a little. Matrix times vector give you what? Vector. Okay, if you don't know, then you should know now. Matrix times vector equals to vector. This one, I did not tell you what it is. Yes, you can claim that it can be a matrix. That's fine, right? But in this context, it's a scalar. So is this correct? Matrix times vector equal to scalar times vector. Any problem? I mean, not correct. Is this incorrect? You don't know, right? As this is not incorrect, because scalar times vector is still vector. Vector equal to vector. So good, right? So here we're saying is that if you can find a vector operated by this matrix, it returns you the same vector, but only scale it by a number. What is the meaning of scaling a vector by a number? Very good. Shrink it or expand it. The direction doesn't change. So basically, these are called the eigenvector and eigenvalue of this matrix. Right? Eigen in German means characteristic. The reason you have this is because it has this characteristic. So this is a very important concept in math and also physics, that you want to describe an object. They have a lot of character. Now you want to describe me, right? First, how many gray hair, how old I am, how long my fingernails. There's so many parameters to describe. But in certain contexts, for example, if you just want to determine whether this is heavy or light, I'm heavy or light, you just need to know my weight. So in that physical context, the character or the eigenvalue, not really this eigenvalue, right? The characteristic value of me is just my weight. How tall I am doesn't matter in that sense, right? So a matrix, n by n matrix has n square numbers. In order to describe this matrix, do you really need to describe the n square numbers, which can be a lot? Let's say 1,000 by 1,000 is like 1 million. Do you need 1 million number to describe this matrix? Yeah, maybe if you want to be exact. But however, the property of this matrix, turn out the mathematician found out that is to find their eigenvalue and eigenvector. This represents its character in the context of linear algebra. Because if, for example, if they apply to the eigenvector, they will only change the size of the eigenvector, but it does not rotate it because the direction doesn't change. So see if you can understand what I mean or think more, but in summary, you need to memorize this. Any vector, any matrix times a vector, if it only scales the vector, then that vector is its eigenvector. Is it okay? Memorize it. And the amount is scaled is the corresponding eigenvalue. Right? This is what you need to understand. But try to understand a little bit what is the meaning of eigenvector and eigenvalue and why they are important, right? So with this, then my goal is to recall, right, review how we find the eigenvector and eigenvalue. And of course, we don't know what they are, so we need to assume the eigenvector E equals to AB. Two numbers, right, can be complex numbers. So what do we get? Then we actually need to solve system of linear equations. 0, negative I 0 times AB equals to a number E times AB. Is this okay? Do you understand how it comes from this one to this one? I just substitute the definition. This is sigma y. E is still E, just a scalar. AB, because I say the vector is AB. That's it, right? And then what do you need to do? Just do matrix multiplication. When I do matrix multiplication on the left, what do I get for the first element? He said minus IB. Do you agree? Because it is 0 times A plus minus I times B. Okay? So that's why you get minus IB. For the bottom one, we repeat the same thing. I times A plus 0 times B. Right? So if you're not familiar with this, please really practice it. Equal to IA or AI. On the right, what do I get? EA. Because that is just a scalar. When you multiply a scalar to a vector, all the coefficient will get scale at the same time, right? How about the bottom? EB. Now tell me, what is this? Is this a scalar, matrix, or vector? Vector, because it's a column vector, only 2 elements, right? And this is a vector. When we say this vector equal to this vector, what does it mean? The requirement is you have 2 equations. You need to have negative IB equals to EA and AI equals to EB. Do you agree? Right? For a vector, if they are exactly the same, you have 2 identical vectors, all the corresponding coefficient needs to be the same. Otherwise, they cannot be the same, right? So I have these 2, right? So I call this, and then I will just further maybe do a little bit more. I'm going to divide the top by bottom. So I have negative IB divided by AI, then is equal to EA divided by EB. I just divide these 2 equations. And of course, E will be gone, I will be gone, right? So I have negative B squared equals to A squared, or A squared plus B squared equal to 1. Right? Because I divide this one by this one and this one by this one, right? Left hand side divided by this one must be equal to right hand side, this one divided by this one. Make sense? And then you cancel I, cancel E. Then I have negative B squared equal to A squared. Then A squared plus B squared equal to 1. Now, this is something that if you don't study, even you get to this point at exam, you will get nervous and you don't know how to solve it, because now you will say, how do I solve for A and B? Indeed, you need to set some assumption, because this one has infinitely number of possible solutions. Okay? So the only thing you need to do is just that you want to make sure that, did I do the right thing? Yeah. You also need to make sure that one more thing. Also, the magnitude of A plus the magnitude of B equal to 1. Why? Because we assume the vector need to be normalized. Okay, so now I want to ask you, is this equation the same as this equation? What is it? Huh? If they are real, they are the same. Yeah. But now we don't limit it to real. Okay, we're doing quantum mechanics. They can be compressed. So where we actually have 2 different equations. Okay, here is talking about the magnitude square equal to 1. But here saying that your square, sum of the square need to be 1 also for this solution. Okay. So that is based on experience, right? So then I naturally would say, okay, what if I assume A equal to 1 over square root 2? Then what will be the value of B? It means B squared equals to 1 minus 1 over square root 2 square, right? Am I doing something wrong? So sorry, I cannot go to here directly. I actually need to use this, instead of using this equation, right? I'm going to use this equation. This is 1, this is 2, right? Then from equation 1, what do I get for B? Negative IB equals to, I did something wrong. Yeah, thank you. That's why I messed up. Thank you so much. You saved me. So, and that's why I got confused. So if minus b squared equal to a squared, then isn't that a squared plus b squared equal to 0? Is that okay? Yeah, and that's why it's completely different from my cheat sheet, and then nothing works. Thank you. Yeah. So based on this, then what is, I don't need to use those two equations. Then what is b in this case? B must be net equals to plus minus, yeah. Can you say again? Minus I plus minus I, right, over square root 2, right? If you just move it to there, right? Am I right? Because b squared will give you negative 1 over 2. And then this is 1 over 2. It gives you 0. How about their magnitude square? Sum of them. They're still equal to 1, right? So that is good. So with this, then I got two vectors, okay? So I have two eigenvectors. What are they? 1 over square root 2, 1i, and 1 over square root 2, 1 negative I. Right? Because this is A. A is 1 over square root 2. And this is B. This is either 1 over square root 2 times I or negative 1 over square root 2 times I. Is that okay? And I jump a little bit, right? So you may say, how come I come up with A equal to 1 over square root 2? Because here you can also, from here, you see that you have A squared divided by B squared equal to 1, negative 1. And then you can take a square root, then you get A over B equals to plus minus I. And due to this condition that you sum it need to be 1, then you can guess that these two are the same. Right? First, they are the same in terms of magnitude, but they need to sum to 1, so this must be 1 over square root 2, just based on experience. Okay? So you need to make an assumption, right? You have something that fit all this equation, and then you can derive it. Because later you find that it really doesn't matter if you add a phase in front of it, because if sigma y times E equal to a number times E, then it's just sigma y times any number times E equal to any number times E, right? I can just multiply a scalar on both sides. Then you actually can have different E. So as long as you scale them by the phase, they are still the solution. That's why you need to pick one. Yeah. This one, because I take square root. Here? Yeah, here I also take the square root. I use this one. So if I have 1 over 2, right? Then b squared equal to 1, negative 1 over 2 on the right. Sorry. This one is confusing, right? So let me write it and then I remove it. I have a squared plus b squared equal to 1. And then I assume a equal 1 over square root 2. That is 1 over 2 plus b squared equal to 1, right? So b squared equal to 1 minus 1 over 2, right? So b equal to plus minus square root the whole thing. 0, I make the wrong mistake again. Sorry. I'm very sorry. 0, 0, 0. So a squared plus b squared equal to 1. This is okay? You see that, right? Because that's when I take square root, I need to put plus minus. Okay. Okay, so because of I'm too slow for this. Yeah. So then here is just some go back and just some extra notes that you can play with. But let me continue on this. So you find the eigenvector, let me call this E0. This equal to E1, right? It has two eigenvectors, right? What is the eigenvalue? In order to find it, you need to plug it back, right? You just plug back to the original equation. For example, one of these is negative I B equal to EA, which is from here. Negative I B equal to EA. So what is C? Negative I, and then B is what? For E0. For E0, what is B? Huh? For E0, what is B? I over root 2. Thank you. Not just I. And then E times what is A for E0? 1 over 2, square root 2, right? Then you cancel it, then you get E equal to 1. That's the eigen. And let me call it E0 equal to 1. Right? Similarly, for E1, I won't prove it. And can you guess what it will be? E1 equals to negative 1. Okay? You try to do it yourself. Now, sorry, because of my problem, I kind of confuse you. But in summary, understand what is eigenvector, eigenvalue, and how you find the eigenvector and eigenvalue. The good thing about this class is usually at most we're doing with 2x2 matrix because it's qubit, right? It turned out to be much easier than what you did in other engineering problem. Yes. Okay, you can consider, okay, so now if you try to consider A equal to negative 1 over root 2, you will also get two set of number. That's two set of eigenvector. They are different from what you have here, but they only different by phase difference. That means maybe by negative I, by plus 1, or by negative 1, or anything e to the power I theta. And this, later you will find that the phase, we call it global phase, doesn't matter. Because this global phase in real experiment will get canceled out. So that is a very good point. So it can be turned out that when you check your assignment, some of you might say, I have 1 over square root 2, negative 1 and negative I, negative 1 and plus I as my eigenvector. It is still correct. If the grader gives you wrong, you should ask for the full score. A very good point. Do you hear what he said? Okay. So you, as long as you just difference by a phase, what we say a phase difference, right? Phase difference, what does it mean? We take this opportunity to learn a little bit more, but in the future we see more. Any vector, whole vector, doesn't need to be the two state. You multiply e to the power I theta. Maybe you forgot, e to the power I theta has a modulus equal to 1. The length is equal to 1. This one in quantum mechanics, in quantum computing, we consider it to be the same as E physically. You cannot replace it. You cannot say, I'm going to remove this. But physically, they are the same. Okay? Because whenever we do some measurement, this one will be gone. Because when we do the inner product. Just take it for granted now, okay? Okay, good. So we've done the